Alright, in this video we're going to be covering a little bit harder material than our previous videos, simply because we're integrating both conservation of energy with kinematics. So the problem we're going to be analyzing today is a ball of mass m that is connected to a massless string of length L that is held out at an angle theta. Once the ball is released, it follows this trajectory. So it moves down and then goes into projectile motion in this trajectory here. Once the string hits the vertical, it stops moving while the mass continues moving. So the first part of this problem, part A, asks, what is the range, delta x, of the ball? So we're trying to find this distance r. And to do this, let's split this system into two isolated systems. I'm going to call this the first system and this the second system. In the first system, we just have the ball being released and hitting this vertical. Right after this ball and the string hit the vertical, we move into the second isolated system. So the first step to finding the range of this ball is to find the velocity that this ball has initially, because we know from kinematics that our delta x, or range, r, is equal to initial velocity in the x direction times time. So the first thing we're going to do is write a conservation of energy equation, and we're going to say that the gravitational potential energy plus the change in kinetic energy of this ball is equal to 0. And we know that this is equal to mgh final minus mgh initial plus 1/2 mv final squared minus 1/2 mv initial squared equals 0. So before we go into what all these variables actually equate to, we have to define a 0 for our system, for both systems. So for this in particular, we're going to define our 0 to be as soon as this mass in the string hit the vertical. So this right here is going to be our 0, and we have a height h below. So let's look at like I said, for this, we're just going to be analyzing the first system. So let's look at what our final height of the first system will be. Well, when this ball is released, it hits the vertical, which is the end of our system. So its height at the end of the first system is our defined 0. So here, this will become 0. For our initial height, we know that if we have this diagram, we can make a right triangle here. If this is hypotenuse of length L, then we can say that this has a side length of L cosine theta. And we know that this height that it drops down to will just be, we'll call it D. D equals L minus L cosine theta, or D equals L 1 minus cosine theta. So the initial height of this ball, when it's right here, is L 1 minus cosine theta. So I'm going to write negative, I'm just going to plug that in for our initial height. Negative mg L 1 minus cosine theta. And we're trying to solve for our final velocity, so let's not do anything with that yet. And we know that this ball is being held at rest initially, so we can say that this goes to 0. So what we have now is this equation. And what we can do is subtract 1/2 mv final squared on both sides, giving us negative mg L 1 minus cosine theta equals negative 1/2 mv final squared. And what we can do now is cancel out the negatives on both sides. And what we're solving for is this velocity final. So I'm going to multiply by 2 on both sides, giving us 2 mg L 1 minus cosine theta equals mv final squared. And now we can see that we have m on both sides of the equation. So those cancel out. And now all I'm going to do is take the square root of both sides. So that we have velocity final equals the square root of 2g L 1 minus cosine theta. Okay, so this is the speed as soon as this ball hits the vertical. So let's keep this equation in mind because we know we're going to need it to find range. All we need now is to find the time. So I'm going to erase this and rewrite my final velocity. So let's keep in mind, when this ball hits the vertical, it's its final velocity of system number 1. But now, to find range, we must look at system number 2 because that's where range lies. So, our final velocity of system 1 becomes our initial velocity of system 2. So, our VF of system 1 is equal to our V initial of system 2, which is equal to what we just found. The square root of 2g L 1 minus cosine theta. Okay, so now to find time. We know using one of our kinematic equations in the y direction that y, our final y position, is equal to our initial y plus initial velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. Okay, so now that we're looking at this second system, we know that our final height must be some height h because we define our 0 here and its total displacement in the y direction is a height h. But here we must define what is positive and what is negative. What direction are we going to call positive? What direction are we going to call negative? So for the purpose of this problem, we're going to call down negative. So in reality, this ball travels a distance negative h from this 0. So I'll label it negative h. So that means our y turns into negative h. At the start of the second system, our y initial, we're at a height 0. So we can cross that out of the equation. And we can assume that this ball is launched completely horizontally so that there is no y component of velocity. So we can cross that out as well. And we know that the acceleration in the y direction, assuming that downward is negative, that our acceleration in the y direction is just negative g. So what we get on our equation now is negative h equals negative 1/2 g t squared. So I'm just substituting negative g in for the acceleration in the y direction, which changes this plus to a negative. So what I can do now is cross out both negatives on both sides. And what we want is t. Remember, our delta x is our initial velocity times t. So let's solve for t. Multiply by 2 on both sides so that we get 2h equals g t squared. Now let's divide by g so that we get 2h over g equals t squared. Therefore, t equals root 2h over g. Okay, so now we've solved for both variables needed to find the range of this ball. So I'm going to erase this and keep the time in mind. So we said that the final velocity of system 1 equals the initial velocity of system 2. And now we have our time is equal to root 2h over g. So now to find range, we must multiply our initial velocity, which is what we have, times t, which we also have. So our delta x, which is equal to r, which is what we're actually solving for, is equal to this multiplied by this. So we have root 2g L 1 minus cosine theta, which is our initial velocity, times our time, multiplied by root 2h over g. So we can see here that we have a g in the numerator, g in the denominator, which cancel out. We can see that 2 times 2 is going to give us 4. So our delta x, or range, is equal to the square root of 4. And remember, we have an h here that must go in. So we have 4h L 1 minus cosine theta. And we know that square root of 4 is just 2. So our range is equal to 2. We can pull the 2 out. 2h L 1 minus cosine theta. So this value represents the range of the ball in terms of the equations, or sorry, in terms of the variables given within the problem.
Okay, so part B of this problem is asking what is the velocity of the ball? What is the v of the ball right before it hits the ground? Right before it hits the ground. Okay, so in the first part of this problem, Logan broke up this diagram into 2 separate systems. To find the final velocity, so the velocity at this point, we're going to treat the whole thing as one connected system. So let's do our energy for this total connected system. We have E total equals the change in potential plus the change in kinetic. And we know that this is equal to 0 because total energy is conserved. So let's expand these change in energy terms. We have mgh final minus mgh initial plus 1/2 mv final squared minus 1/2 mv initial squared. And this is equal to 0. So we still have our height to be defined as 0 at this point, right when the ball disconnects from the string and is going into projectile motion. So let's look at these individual terms. What is our final height? Because we know that our height is 0 at this point, once our ball reaches the bottom, it is going to be a negative h height from that 0 point. So our height here is negative mgh. All I did was bring the negative from the h out to the front. Minus, and our initial height we found in the first part is just L1 minus cosine of theta. So we get minus mg L1 minus cosine of theta plus, what is our final velocity? Well, that is what we're trying to find. So 1/2 mvf squared. And the initial velocity of this system, well, remember that our ball is initially being held out at some angle. So our initial velocity is going to be equal to 0. So we can take away that term. Okay, so let's bring this velocity term to the other side so we can try to solve for it. Rewriting what we have here, we have negative mgh minus mgl 1 minus cosine of theta is equal to negative 1/2 mvf squared. Okay, so now nothing changed in these terms, I just brought them down, but you see that we have m's on both sides of the equation. So we can cancel out these m's, giving us negative GH minus GL 1 minus cosine of theta. And remember, this was just the height that we found in the first part. And this is equal to negative 1/2 velocity final squared. Okay, so let's get rid of this negative 2. Let's multiply both sides by negative 2, or negative 1/2. We're going to multiply both sides by negative 2 to get rid of that. So we have 2GH plus 2GL 1 minus cosine of theta is equal to our final velocity squared. So now let's just take the square root of both sides. We get that the square root of 2GH plus 2GL 1 minus cosine of theta is equal to our final velocity. So in this part, in the second part of this problem, part B, we had to treat this whole system as one connected system, where in part A we had to break it up into 2 individual systems in order to help dissect the problem. So the final velocity that this ball has right before it hits the ground is equal to this, the square root of 2GH plus 2GL 1 minus cosine theta.